Good morning, everybody. Ladies and gentlemen, dear Deputy Head of the German Embassy, Beisert, dear panel, dear colleagues from near and far, it is a great pleasure to welcome you all today to our 8-year symposium, Frontiers in Climate Physics. My name is Axel Timmermann and I'm the founding director of the IBS Center for Climate Physics, short ICCP, a hub for integrated Earth system science. It is a pleasure to invite you today on a little journey into who we are and what we have accomplished in the last 8 years. Our center saw the light of day in January 2017, so 8 years ago, and currently our 54 members from 12 different countries, they actually work in this building on the 10th and 11th floor, where we have our lab space, isotope geochemistry lab, our office space, as well as 2 seminar rooms. In our center, we have 6 professors, 6 faculty members with expertise ranging from climate physics to monsoon dynamics, atmospheric dynamics, advanced statistics, oceanography, climate modeling, and marine biogeochemistry. And in 2018, our center, together with the IBS headquarters center in Daejeon, purchased the Aleph supercomputer. It was one of the fastest computers in South Korea at that time. And subsequently, we bought additional mass spectrometers that help us to reconstruct past climate change using stalagmite samples from all over the world. So we are proud of the diversity in our center. And over the last 8 years, we had 100 members from 17 different countries, and the majority of them were women. So here you can see the main research themes in our center. This is Earth system modeling, Earth system dynamics, sensitivity, predictability, Earth system history, and climate, life, and carbon cycle. And the center is operated, managed by one director, that will be me, an administrative support team, and a technical support team. And we are very grateful for the input from our scientific advisory board over the last 8 years. So these research themes, they are aligned in such a way, they are designed in such a way that we optimize the collaboration amongst these research teams. Our mission is to enhance the understanding of natural climate variability and anthropogenic climate change in general in response to different types of forcings, and to improve the ability to simulate, predict, and project climate impacts on various components in our Earth system, such as the atmosphere, the hydrosphere, biosphere, and the anthroposphere. And so we are particularly interested also to understand how climate impacts ice sheets and the corresponding influence on sea level, life, planetary health, and also regional processes. So these research themes and the research mission, they are addressed by using various types of methods. So we use theoretical approaches, numerical modeling, we go to cave systems and do observations in these caves, and we have a lab where we use analytical tools to reconstruct past climate change. So the research in our center revolves around 8 main objectives. One is to understand the drivers of natural climate variability, to identify the sensitivity of Earth to various types of forcings. We're also interested in looking at the predictability 1 to 5 years ahead of the climate system, not only the longer term projections. We would like to improve climate models, and in particular also information about future sea level rise. Elucidate how climate influences life on our planet, both terrestrial and marine life. We reconstruct, as I mentioned, past climate change using stalagmites from caves in the world. We train the next generation of scientists, and what's very important for us also that we share our information with the general public. So these research objectives and the research themes, they are essentially aligned to really optimize our holistic perspective on the climate system. And they're infused, if you like, with the ICCP philosophy to conduct transdisciplinary research, transformative research, high impact, high reward research. We are also looking at the Earth system as a continuum from the past to the future, not just one particular snapshot. We combine various tools, and from rock corer essentially to supercomputer, we use a variety of different methods. And as I mentioned, we really would like to share our information with the general public, policymakers, media, and schools. So in the last 8 years, we published more than 340 publications. 75 of them were published in journals with an impact factor larger than 9. And so among them, 12 in Nature Climate Change, 13 in Nature Communication, 8 in Science Advances. And in particular, one of our main research outcomes were 3 publications, main authored publications in Nature, and 3 of them in Science in 2023. So just to give you an idea, where do we stand? So I looked at the number of publications in high-profile journals. That includes, for instance, Nature Science, Nature Communication, Science Advances. So these are more general publications. And so there, in comparison with other climate research centers, and you may recognize some of these acronyms here, we are doing quite well. And also in terms of the percentage of papers published in Nature and Science, I think we are also on a relatively good position here. Okay, so if we look at our research network that we have built in the last 8 years, I'm very proud to see that we have essentially created a network of scientists, very close collaborators, both domestically with main research institutions in South Korea, but also internationally, and I only show some of the main research collaborators here. Researchers from our center, they are heavily engaged in the international community. Professor Jeannie Lee, for instance, she was the coordinating lead author of the AR6 report of the Intergovernmental Panel on Climate Change. Professor Kyung Jaha was the president of the Korean Meteorological Society. We have some of our members as editors in main EGU journals as well as Springer journals. We give advice in a capacity as scientific advisory board members to the Alfred Wegener Institute, IBS Center, and also the Korea Polar Research Center. So the IBS has a really nice motto, and that is making discoveries for humanity and society. And I like that very much. So we take it very seriously in our center, where we essentially try to deliver important data, of course, to the scientific community, but also to potential stakeholders, schools, the general public, media. How do we do that? Well, we have a climate citizen science program called Korea Water Isotope Network. We give public lectures regularly, collaborate with science museums across the country. We issued 27 press releases in the last 8 years. And of course, many interviews in response to that from radio, TV, and newspapers. We were featured in several documentaries, wrote several popular science books, as well as a textbook for high school students on climate and environmental change. And together with the German embassy, just to give you an example, we organized a climate roundtable discussion with climate activists from Seoul and the German President Walter Steinmeier. So just to give you an idea, our graduate students are now a part of the Department for Integrated Climate System Sciences. And this department has become a part of a new school here at Busan National University, which is called School for Carbon Neutrality and Climate Change. And our graduate students, of course, they are supervised by the faculty in our center. So we have a very close linkage between training, education, as well as supervision. And also our graduate students have access to all these computing resources in our lab. So I mentioned already some of these highlights here, ICCP in a nutshell, but I wanted to point out over the last 8 years, 14 of our students either got a master or PhD. Many of our scientists receive international awards and also domestic awards. We organized 3 major conferences, IBS conferences, 5 workshops, 1 hackathon, and we hosted 140 seminars in our center. So looking back at these last 8 years, I can say I'm very grateful to an incredibly enthusiastic team of scientists and also staff members. So it has been an incredible journey, and I'm looking forward also to new adventures in the future. So I'm sure now you're burning to hear a little bit more about our science highlights. So I will be talking now about simulating climate and its impacts on humans. Okay, the following talks then will be on Asian monsoon and heat waves, climate extremes in a warming world, climate life and carbon cycle, and that covers a broader range of research subjects in our center. So looking back at the first 5 years in our center, after we got the access to the supercomputer Aleph, we started to embark on a number of high-resolution computer model simulations, in particular using the Community Earth System Model, short CSM, at a 1/4 degree atmosphere and a 10th degree ocean resolution, and we ran past, present and future simulations. And that gave us new insights into mesoscale processes both in the ocean and also in the atmosphere. Then, together with the National Center for Atmospheric Research in Boulder, Colorado, we ran a large ensemble. This is a set of 100 computer model simulations using a newer version of the CSM model. And we are looking at the time period from 1850 to 2100, following a particular greenhouse gas emission scenario. And the nice thing with this model simulation is that every point in time with 100 different realizations of the climate system, which allows us to estimate the probability distribution of the climate system and how it changes over time. We use also an isotope-enabled model version, and the data from these computer model simulations can be directly compared and linked with data from our isotope geochemistry lab. We also completed or coupled the CESM model with an ice sheet, both in the northern and southern hemisphere, ran fully coupled glacial simulations, and we conducted the longest climate simulation to date, covering the Earth's history of the last 3 million years. And this is an important simulation that I will mention later on again. Ecosystems, well, we are very much interested in the impact, of course, of climate change on life on our planet, and also humans, how early humans essentially responded to that. So for that, we developed hominin dispersion model and a human habitat model. So hominin refers to a different human species. Okay, then in the last 3 years, we kind of shifted gears a little bit, focusing more on high-resolution storm resolving computer model simulations at 9 kilometer, and now actually as of last week also 4 kilometer resolution. So these are global warming simulations at a very high resolution, and that allows us really to study regional processes in much more detail. The model that we're using for this is not NCAR CSM anymore, but the Alfred Wegener CM3 model. And that model is computationally extremely efficient. It's based on essentially the ECMWF model and a German ocean model. Okay, so 2 weeks ago we published a paper that looks at the impact of killer asteroids on our climate, but also on life on our planet. And there is one particular asteroid that has a very high chance to hit Earth in essentially 2182 CE. And we wanted to know what's going to happen if that occurs. So this was featured in the Washington Post and so on. We also finished a simulation on essentially multi-year predictability, where we study how predictable are certain variables in the climate system, maybe 1 year, maybe 2, maybe 5 years ahead. And we ran essentially a computer model simulation for vegetation changes over the last 3 million years. This is important because this information also goes into our ecosystem model. We developed a new dynamical vegetation model coupled to a mammal model. I'm going to show some results on this. We also used an agent-based model with DNA. So humans run around in the world and we can track their DNA in response to climate change. And this is a new feature. So here you can see, for instance, the biomass changes of reindeers over the last 40,000 years, just to give you an example. Okay, let's focus on some of the highlights here. This was just the modeling portfolio, climate dynamics and sensitivity. So let's start with El Nino. And we know every El Nino is different. Some of them occur in the Eastern Pacific, they are stronger. Some of them in the Central Pacific, they are usually a bit weaker, but they have different impacts on the weather worldwide. So this is very important to understand. So in order to understand if there is a way to understand the complexity, we invited El Nino experts to our center and wrote a review paper for Nature where we present a new, if you like, blueprint, a new understanding, robust understanding framework for the complexity of El Nino. And what we found is that using a simple atmosphere-ocean model, looking at the mathematical structures, the oscillatory modes, the eigenmodes of the equations, we find two very similar modes, so Eastern and a Central Pacific mode, and also they occur for very similar conditions. So this is for strong winds, this is for weaker winds, and the same we also find in the observations. So this is a nice way of boiling down, condensating the complexity of El Nino to essentially mathematical structures in the equations. Of course, there is noise in the system making it a bit more complicated. Okay, let's take a look at this one. We have El Nino, of course, responds to these background changes, and we want to understand what are the drivers of these background state changes in the equatorial Pacific. What you can see here is essentially what happens to our surface temperatures if we increase the CO2. This is for a quadrupling in the climate model. This is very well known, and there is this enhanced equatorial warming strip. Outside the equator, we have less warming. And this is very well known. So we wanted to know, where does this warming pattern actually come from? And we ran a computer model simulation where we only prescribe, is idealized of course, CO2 in the equatorial Pacific. And what you see is the warming itself is much, much weaker. So the local CO2 forcing, the local processes are not the main driver for this warming. However, if we prescribe the CO2 idealized only in the off-equatorial regions, we see a much stronger warming. Well, that was a bit of a surprise, because it says that remote processes control essentially the climate conditions on the equator. How does that work? Well, the equatorial forcing itself, in this case, strengthens the Hadley cell. And if the Hadley cell strengthens, we have more wind convergence towards the equator, and also more cold water is upwelled, and we have stronger negative cloud feedbacks. However, in the case of off-equatorial forcing, we are weakening the Hadley circulation, so it's spinning down, and we have less cold water being sucked up by the winds from the ocean, and we have less negative cloud feedback. So we have a stronger warming. So that says that off-equatorial processes, remote processes, play a key role in shaping essentially the global warming patterns on our planet. This is interesting because changes in the climate background will also change the variability. And this was featured in a recent study where we looked at this large ensemble that I mentioned earlier on, 100 model simulations into the future. And in shading, you can see the main variability. So there is El Nino variability here and so on. And the blue and red dots indicate where in future the variability will either decrease or increase respectively. So we have this for temperature and for precipitation. Just look at the number of blue dots. So in future, variability in temperature on average will decrease on our planet. This is kind of interesting. Then for precipitation, it's the other way around. Future variability will increase. And so we can try to understand where this is coming from, but we can also split this up, in particular going back to the El Nino problem in this area, where essentially, if we look at the spectrum, how this changes over time, for present day conditions, we have this blue spectrum. In future, El Nino peak will be a little bit shorter, but overall there is a slight suppression of the variability. If we look at the power spectrum for precipitation in this area, we see on all time scales, essentially, we have an increase in the variability. This is very important for impacts worldwide and so on. So this is a way of looking at the effect of climate change on the variability in the climate system. And this is, of course, also interesting in the context of other extreme events. Well, in particular, tropical cyclones, or typhoons, as we call them here, hurricanes somewhere else. And we used this high-resolution computer model simulation, which actually resolved these flying donuts with an eye wall also in the middle. And so they are quite well resolved and interact also with the ocean. Now we ran future simulations with this, and what we find is that overall globally, in response to CO2 increase, the frequency of these events will decrease. However, once they emerge, then there is a much higher likelihood for them to become stronger, larger than category 3. So this is a really important result. And also every tropical cyclone in future, because the atmosphere holds more moisture, can dump much more rainfall when it makes a landfall. So up to 12% more rainfall for a doubling, and much more, of course, if CO2 went up further, which we actually don't know. Okay, so this gives you an idea of these tropical cyclones, but tropical cyclones, when we think about them, we think about, well, TV images, their destruction and so on. But these guys have been around for millions of years on our planet. But so far, very few people have looked at how past climate change influenced these very powerful systems that also change mixing in the ocean and other shaped coastlines and so on. So we ran a computer model simulation, again, very high resolution. But now we are looking at the effect of changes in Earth's orbit and Earth's axis, so-called Milankovitch cycles, on these tropical cyclones. And what you can see, this was the previous figure, essentially reduction in response to future climate change. If we compare the summer perihelion conditions, northern hemisphere summer perihelion conditions 125,000 years ago, with the aphelion conditions, so two extreme cases, we see a completely different pattern. So, of course, we have stronger tropical cyclone frequencies in the extratropics, in the subtropics, and so on. But interestingly, if we go a bit more into the details, the main mechanism for these changes, even though the pattern looks very different, is quite similar. And it turns out there are many different factors controlling, of course, tropical cyclones. But here, in this particular case, in both past and future simulations, the humidity changes and moist entropy deficit changes play a key role in determining this structure. The changes in sea surface temperature, wind shear, and so on are less important for that. So that's something to keep in mind. Now, we'll stay a little bit in the past and look at the effect of past climate change on humans. So here we are looking at the last 2.5 million years. The color indicates the temperature. Overall, there was a cooling, and we see that the glacial cycles become stronger, of course, in response to Milankovitch cycles, but also a decrease in atmospheric CO2. So this is essentially the time period when our genus Homo emerged, with many different species. We call them hominins. But, well, currently there is only one left. All the other human species essentially disappeared from our planet. And that's, of course, us sitting in this room and elsewhere. So we wanted to know, what role did climate and this intensification of the glacial cycles actually play in this human evolution? And for this, we ran, I mentioned already, this simulation that covers the Earth system history of the last 3 million years. And what it has included are changes in greenhouse gases estimates, changes in the ice sheets in the northern hemisphere, changes in the orbital forcings, the Milankovitch cycles. So it's a very comprehensive simulation, and we compared it with paleo data, sediment cores, ice cores, and so on to really see how well does it work. And it does extremely well. So then we can also use the temperature, precipitation, solar radiation data to force other climate models, such as a vegetation model, or also other human models and mammal models with these data. And that's kind of important because it gives us some idea on the effect of climate change on human evolution. So how do we do that? Well, assume we have a database, and we have one of these databases for the different human species. Let's say we know where this skull was found, how old it is, so we can essentially, and for all of the existing artifacts, we can have the location, we have the time, we can look in our climate model simulation, what was the temperature like at that location, at that time, the precipitation, and we can build a statistical model that calculates the probability of human presence for a given set of climate variables. Or, because the climate changes in our climate model simulation, as a function of time, we can directly calculate for each location and each time, we can calculate the habitat suitability and estimate of the human presence probability. So let's take a look at Europe here. for instance, calculated from this habitat model. And we're looking here at one particular species, Homo heidelbergensis, from 600,000 to 300,000 years ago. And these are Neanderthals. They disappeared, of course. And so we see essentially both of them have the same habitat suitability. They are essentially the same in terms of this environmental preferences. This could be a good indication for this species actually being the mother species and this the daughter species. This could be an indication for an anagenetic gradual species transition. So let's apply this also, and we can see also the Milankovitch cycles. So human habitats were affected, of course, by the climate. Okay, so we can now try this for our own species. Homo sapiens emerged in Africa somewhere around 200 to 300,000 years ago. Still, it's unclear whether it was Eastern Africa, whether it was Southern Africa, or whether there was kind of a multi-regional origin. Well, and we can check this because if there was a speciation from the mother species to the daughter species, they should have been in the same, they should have had the same environmental preferences at the time of the speciation. We look at Eastern Africa and there is a large gap there, so that is not a suitable area. If we look at Southern Africa, the species essentially transition is quite smooth, and so the mother species, which is Homo heidelbergensis in Africa, is very likely taking place, the speciation, in Southern Africa. And this is also consistent essentially with another study that we published in Nature together with some geneticists. So if you wonder who this mysterious ancestor of Homo sapiens was, I brought one for you here today, so you can take a look at this. So this is Homo heidelbergensis. The jaw is missing, of course, but these are essentially our ancestors in some way. Okay, so let's move on. So if we look at this habitat, this is actually quite interesting. Habitat overlap between different species. We did asked another question. There are Neanderthals in Eurasia, but there was another more elusive species, the Denisovans. They were quite famous because they are genetic species. And we found out, building these habitat models, that Denisovans preferred more colder, more boreal forest environments, whereas Neanderthals, they actually liked warmer conditions and essentially temperate forests. Now it turns out that whenever we have an interglacial high CO2 conditions, these habitats start to merge, which is a prerequisite essentially for interbreeding to take place. So we calculated when do these habitats essentially merge, and it turns out this happens when we have very warm conditions, and there are corridors where potential interbreeding may take place. And it turns out if we compare this with paleogenomic data, there is a very good match essentially between what the climate model essentially tells where this habitat would have happened, overlap would have happened, and the genomic data. So this study was published in 2023 in Science, and it gives us an idea that climate in some way is a matchmaker in this human love story in some way. Okay, so I wanted to stay with this human interaction climate story. And sorry, this is an equation, but I will explain it very briefly. So we know that Neanderthals went extinct. Well, we still have Neanderthal DNA in us. And there is a question why? Why 38,000 years ago? And there are three main hypotheses. Some people argue it was past climate change, rapid climate change. Others argue, well, they were just assimilated in the more successful, more populous Homo sapiens population. And another one is competition with Homo sapiens. Now, what we have here is that an equation that describes the change in the density or number of individuals is due to diffusion, dispersal, if you like, birth, how many individuals are being born. Then we have competition and food, so this is a mortality term, and we have the interbreeding between two different species, let's say Homo sapiens and Neanderthals. And it turns out many of these parameters are actually rather well known. We have information on the interbreeding rates and so on. What we don't know very well is, well, the carrying capacity, and I'll come back to that later on, and this is the food resources. So we obtained an estimate of the available food resources for these two different species they compete for. from another climate model simulation. And let me show you the result. So the result here, we see the Neanderthal population. Actually, there is a simulated extinction 38,000 years ago. We can change millennial scale abrupt climate change. It doesn't do anything. So the first hypothesis is gone. Then we played around with the interbreeding rates within a realistic range. And also this one did not change the final outcome. So it turns out that the competitive exclusion of Homo sapiens, the pressure on Neanderthals, taking away the food resources is the main reason why we have this, extinction. We can see that here, essentially 55,000 years ago, Homo sapiens oozes out of Africa into Neanderthal land. These are archaeological sites. And you can see as Homo sapiens emerges in our model simulation, also the Neanderthals start to disappear. So you may wonder, why is it so powerful? I mean, the densities at that time may not have been very high. There are different possibilities. We are currently working on a virus-induced extinction idea, but there is another interesting one, and this is because we can say maybe Homo sapiens had a higher culture level. Now, how can we simulate culture? And this is something I wanted to show to you here at the very end. So simulating culture and climate sounds very adventurous. You think, okay, culture is a soft thing, but there is something interesting here. Let's start with this logistic equation where we have a change in the density or number of people due to how many people are born and how many people die. And there is again this mysterious carrying capacity, which is an indicator for food resources. So if K is very large, lots of hamburgers, then this number is actually quite small, which means we have less mortality. Maybe hamburger was not a good example because that could go the other way around. So clearly, if this term becomes 0, which happens when the density equals the carrying capacity, then this term is a stable situation and we have essentially a stable population. Now, this carrying capacity, imagine you have two groups. One group that is very good in hunting and another group that is not very good in hunting. So for the same food resources, the group with the higher hunting skills will be able to maintain a larger population. And this is essentially the interpretation that we propose here, that culture is a booster for this carrying capacity. We call this cultural carrying capacity. So now, we also need an equation for how this culture changes over time. And that is even more adventurous. But you can think about it. The change in culture is due to, well, innovation. And there is a random factor to innovation. Of course, we don't have an Einstein every year, so there is a randomness. But there is also this loss of culture. So essentially, if we stop talking to each other for the next, generations, we will lose culture because we don't communicate culture. So communication is very important. And then you can essentially argue that the innovation itself, even though it has a random term, the larger the group we have, the more innovation there will be because we can learn from each other. We can combine knowledge. We can synergize our knowledge. This is called the connected brain or cultural learning concept. So, which means that the rate at which innovation takes place depends on the density itself. So now we have two equations that we can simulate. We can run essentially a model where we have the innovations and over time culture integrates. Right? And it looks like the stochastic climate model of Klaus Hasselmann, except for this rho term here. So we have this idea in there. Now let me just show you a little example where we are going to introduce all of the realistic features that we have understood so far. Changes in habitats, I mentioned earlier on, changes in the vegetation, but also changes in the vegetation type biomes, and we introduce culture. So we will simulate the behavior of 3 different human species, Neanderthals, Denisovans, and Homo sapiens. And well, let's just run it. So Homo sapiens, I will show you, they will leave Africa around 60,000 years ago. Okay. Oh, right now, okay, and you see, whoops, all the others are gone. So what did we do here? The demographic parameters, birth rate and so on, in this model are essentially the same amongst the 3 different groups. They have different habitats. The only difference is that we give Homo sapiens a slightly higher innovation rate. And over tens of thousands of years, because of the last equation, the culture integrates. And that creates this competitive exclusion. So this is a different perspective. And I just wanted to close here very quickly by looking at some of our future directions in the center. We cannot only simulate humans, but we can also simulate other mammals. So we built a computer model that simulates 2,171 mammal species on our planet. If you're interested, I can tell you more about it. And the nice thing is we can look at the effect of climate change, past but also future climate change, on extinctions. And we can look at how much does the functionality of an ecosystem depend on the climate conditions. Diversity, multiple equilibria. Essentially, we want to understand the impact of climate change on climate and evolution. So what you see here is just a simulation. Mammoth is a nice species. We are seeing the biomass changes over the last 40,000 years of mammals. And of course, mammals now are extinct. Mammoths, not mammals. Mammoths are now extinct because of overhunting. We can also look at the species diversity and other ecosystem parameters to better understand how climate influences ecosystem complexity. This gives you just an idea of the research breadth of that could be opened with this type of new research model. Okay, so I will close here, and I'm happy to take your questions. And on behalf of the IBS Center for Climate Physics, I thank you all for coming and for your interest in our research.